Hi, we are Santiago Villarreal and Arthur Sluÿters from Université Catholique de Louvain, Belgium. We present our paper Theoretically Defined versus User-Defined Squeezy Gestures. Shape-changing interface enable end user to interact with digital objects whose shape can change based on the user action. Either as input, for example, by measuring how much it gets deformed, or as output, for example, by providing resistance. This paper focuses on squeezable interface, a specific type of shape-changing interface where the interaction is based on a tangible object whose deformation can serve as an input. To this end, four main parts of the object can be exploited: their surface, their volume, their position in the space, and their sensitivity to deformation when some pressure is applied. We define a squeeze gesture as any pressure action exerted with or on a squeezable object, sometimes in combination with a movement of this object that causes a detectable form change of any part of it. They can take several forms, such as stretching, pinching, folding, or freezing. Squeezable UIs exist both in the industry and in research. The edges of the HTC U12 Plus smartphone are sensitive to pressures, which made it possible to generate a squeezy gesture, even when the smartphone is turned off. Another example is Squeezy, which is a complete system for deploying a squeezable interface. It includes both hardware to record deformation and software for recording squeezy gestures. However, little exploration has been done regarding how this gesture could be effectively designed and mapped to various tasks. All research attempted to fill in this gap. To this end, this paper has three main contributions. First, we investigate how to collect, analyze, and understand user preference for squeezy gestures. Second, we contribute to the gesture elicitation methodology with insight on what theoretically defined squeezy gesture could inform empirically derived one. Third, we suggest some implications for designing squeezy gestures.
As a first step, we define a taxonomy of squeeze gestures consisting of four main categories. The first category are 0D gestures, which apply pressure on one or several points of the object, for example, pushing at the center of the object. 1D gestures press one or multiple lines of the object. For instance, a wipe push consists of imitating a windscreen wiper while pushing on the object. Then, 2D gestures press one or more curves on the object. For example, the dual line push consists of producing two connected line segments. Finally, 3D gestures consist of any motion in space of the squeezable object, such as folding it. We then conducted a gesture elicitation study with 32 participants, aged between 18 and 80 years. Most participants regularly used computers and smartphones, but none had ever used a squeezable device. We asked them to propose gestures with a squeezy-enabled cushion for 21 IoT tasks, such as turning lights on and off, controlling the TV, answering the phone, and so on. We identified a wide range of gestures which were clustered by similarity. Tasks such as turn TV on and turn TV off resulted in a very high agreement between the participants, while other tasks such as turn aircon on, mute, or unmute had very low agreement, probably because of their different levels of familiarity. Gestures were applied on different parts of the cushion depending on the task, such as turning the TV on or off, which was mainly performed in the middle of the cushion. Many gestures also involve the top and right side of the cushion. From these results, we suggest some implications for designing squeeze user interfaces. Push and fold gestures were the most frequently proposed gestures by the participants and are easier to perform and capture than the slightly less popular draw and swipe gestures. They could therefore be promoted. In addition, when participants performed gestures using both hands, they were always symmetric. Consequently, we advise to prefer symmetric bimanual gestures instead of asymmetric ones. Our work has some limitations. First, the cushion used only represents a single category in the non-rigid human-computer interaction framework. Other squeezable objects of different shapes, sizes, weights, or textures were thus not considered in our study, but could be. Second, the referents used covered discrete actions, such as turning an object on or off, and linear actions, such as increasing or decreasing some property. However, they did not cover genuine 2D or 3D actions, such as moving an object in space. Third, our theoretical analysis in the form of a taxonomy and empirical analysis in the form of an elicitation may not have uncovered the complete set of possible squeeze gestures, so some may thus be left to discover. To conclude this presentation, we compared theoretically defined squeeze gestures and user-defined squeeze gestures, namely to identify which parts of the taxonomy were actually used in the experiment. We determined the theoretically defined squeeze gestures by conducting a systematic analysis of gestures based on their dimension, which resulted in a taxonomy of 82 gesture classes. For the user-defined gestures, we conducted a gesture elicitation study with 32 participants to come up with a set of squeeze gestures for 21 actions. For more details, including the full results and implications of our gesture elicitation study, please refer to our full paper. Thank you for listening to our presentation. Any questions or comments about our work are very welcome.